Wisconsin-Madison, here to tell us about n-periodic homomorphisms and periodic structure.
Thank you all for being here. Can someone hit this, like, the light so that the front row of lights is off? By any chance? I think they're around the back, yeah. I have a lot of colors on my slides. I need them to pop. I need people to appropriately appreciate them. Which might be a little bit easier if these front lights are off.
It's one or the other.
Is it all or nothing? Oh, you're up here. Ooh, yes. Fantastic. Okay, thank you so much. Well, thank you so much, everybody, for being here. Thank you to the organizers of this conference for having me. I was talking to Dave earlier, or I guess yesterday, about like how special it is that I was invited to give this plenary talk, because this has been one of my favorite conferences to go to since I was a graduate student. I feel like it was one of the first places that I really felt like comfortable, like mathematically, and that's especially due to Dave, who like has always been like such a warm host whenever I visit Temple. So I just want to say like very much thanks for that. I also was back a couple years ago as a panelist, so it's pretty nice to complete this cycle now as a plenary speaker. So today I'm going to tell you a little bit about my work on n-periodic homeomorphisms. In particular, I'm going to tell you about n-periodic stretch factors. And so the structure of my talk is in 3 parts. I'm going to start off by telling you a little bit about what happens in the finite type setting with pseudo-analytic homeomorphisms. And then talk about sort of switching to the infinite type setting, talking about n-periodic homeomorphisms and trying to draw some parallels between the two. And then we're going to end the talk by talking about stretch factors. And if you were in the plenary talk yesterday, some of that might look a little familiar because this is sort of related to topological entropes. Okay, so we're sort of back to some dynamics a bit. Although the first part of the talk will be sort of very topological, sort of geometry topology. Okay, so let's start off in the world of finite type surfaces. Okay, so these are surfaces. I'm only going to be thinking about closed orientable surfaces. Finite type just means that they have finitely generated fundamental group. And I'm really going to be sort of sticking to the world of hyperbolic surfaces, so genus 2 or higher. And so this is sort of the setting for this first third of the talk. And the star of the show is going to be pseudo-analytic homeomorphisms. Okay? So this is a bit of a mouthful. I'm going to say the definition, and then I want to talk through the pictures, which hopefully will elucidate this if you haven't seen it before. So I'll say that a homeomorphism F is pseudo-analytic if there exists a pair of singular transverse measured foliations. The unstable and stable foliations that I've denoted by like FU and FS, they're measured, right? So they are pricked with some measure, such that they are preserved by F. So F of them, the foliation itself is preserved, and then the measure is either stretched or contracted. Okay, and so this stretching amount, lambda, this is some real number greater than 1, and this is called the stretch factor of my map. Okay, so again, if you haven't seen this before, what should we think of when we think of a pair of singular transverse measured foliations? I want you to think of this sort of picture down here about what it looks like locally. Okay, so locally, away from the singular points, it's just going to look like sort of the induced foliations that you would think of if you like take like the horizontal and vertical like lines in the plane. Okay, so we have this this foliation here. Towards the singular points, it looks a little bit more complicated. Right here, I have a 3-pronged singularity, but still my foliations are coming together transversely. Right, you're sort of seeing only transverse intersections. And so then the action of them, I tried to illustrate this over here on the left. Is in this example, I've shown that we are stretching along the blue and contracting along the red. Okay, so you can see like I colored in those like little yellow and green squares or rectangles, and you can see that they're getting sort of shrunk down in one direction and stretched out in the other. Okay, so this is the sort of thing to think about when you're thinking about the action of a pseudo-analytic. You have this sort of local picture. Where did I go? Did I clicker? Okay. I should also mention, please feel free throughout to stop me and ask questions. I'm happy to take questions at any point. You don't need to hold them to the end. Okay, so these are pseudo-analytic. A fantastic question.
Thank you so much for inviting questions. Sorry if this is you can save this for later if it's too basic, but can you just say what it means for the foliation to be measured?
Yeah, so I just want, I want to be able to talk about what it means to stretch or not, right? So these foliations, in this picture, when I've drawn these as like sort of all of these disjoint lines, but they are actually completely filling up my surface, right? So that every single point, I'm in some leaf of my foliation. And so I need to say what it means to sort of pull them apart and trig them. And that's just what my measure allows me to do, okay? Yeah, awesome. Other questions? Okay, fantastic. So I can think of these, sort of another way to think about this. I said, right, like you can sort of think about them away from the singular points as just sort of being induced by like a vertical and horizontal foliation in the plane. And here's a very precise way of thinking about that. I can take, for example, a polygon in R2, right, and I can endow it with the vertical and horizontal foliations. And in this case, right, this polygon, if I glue up the opposite sides, this is going to actually give me a genus 2 surface with a singular point with angle 6 pi, which comes from sort of the identification of all those vertices. So that's something, if you haven't seen this before, that's something you could sort of actually work out on your own if you're interested. And so you actually get sort of this singular point here with this sort of 3-pronged singularity, and everywhere else it'll look like this, okay? So this is actually now a singular flat structure that I'm endowing my surface with. And so another way of thinking about or describing a pseudo-Naso, if you want to sort of leave that foliation language behind, right, so you glue up and you get this, and you can say this is a flat structure invariant under F. And so it's not, every pseudo-Naso homeomorphism has an invariant flat structure. So that's sort of another way to think about this. Okay, so I sort of gave you this definition. I'd like to show you that this definition is not vacuous and give you an example of a pseudo-Naso homeomorphism. And sort of the most straightforward way of building pseudo-Naso homeomorphisms is using Dane twists, okay? So these are maps of my surface, which I sort of always describe by just drawing a simple closed curve. So this is some closed curve that doesn't intersect itself. And so when I draw that closed curve, I'm thinking about sort of the associated map, which is going to be the one where you cut open along your closed curve and you hold one side still and you twist the other by 2 pi and you reglue, okay? And so here I have a Dane twist along a single curve, this T beta, right? That's just the Dane twist about beta. And then this TA is just, I'm going to think of taking the product of the twist along alpha 1 with the twist along alpha 2 and the twist along alpha 3, okay? And so the thing I've shown here is a way, this is a construction of Penner for building sort of a lot of examples of pseudo-Naso homeomorphisms, where I start off with some sort of collection, a pair of multi-curves that sort of fill some subsurface, and then I compose with a shift. So here my shift row, I'm just thinking of sort of taking every genus and clicking it over by 1, okay? And so it's a result of Penner that if I sort of raise this to a high enough power, in particular, sort of a high enough power so that as I sort of click around, I'm filling up my surface with these simple closed curves, my resulting map is pseudo-Naso, okay? And so this is often described as like a phone dial. So this is like a way that you can sort of remember this type of picture. So suffice it to say, there's sort of lots and lots and lots of examples of pseudo-Naso homeomorphisms, even though, right, on first glance, that it's a very strong thing to have this sort of underlying invariant structure. Okay, so I care about pseudo-Naso homeomorphisms in the context of the mapping class group. So this is the group of orientation-preserving homeomorphisms of my surface, S up to homotopy. And so when I think of a mapping class, right, I'm thinking of now a homotopy or isotopy class of maps. And so when I say that a mapping class is pseudo-Naso now, I just mean that there's a representative homeomorphism that has these pairs of invariant foliations or this invariant flat structure, right? So it's not that sort of every map in this isotopy class will satisfy this, but there's a representative one. Okay, so that's what I mean when I say like a pseudo-Naso in the mapping class group. And it turns out that we have a really nice classification of what different elements of the mapping class group can actually look like. And they essentially come in just 3 flavors. Okay, we have the finite order things, and so this is sort of finite order that you think about it in any group. It just means you raise it to some power and you're the identity. We have things which are reducible. This is a little bit maybe different than you might have seen. This just means that there's like some, actually let me go this picture. There's some collection of pairwise disjoint, simple closed curves, which are invariant under my map. So for example, if I take this fidget spinner and I do a rotation by 2 pi over 3, right, this is both finite order, right? After I click around 3 times, I come back to the identity. It's also reducible because this sort of collection of curves are just permuted, right? Another example is the one that I just mentioned, I didn't draw a picture of, right, is the Dane twist. Here, this is something, so if I do a Dane twist, maybe it's hard to see what this is, but like let's twist this curve, right? The image of this curve under twisting by the purple one will look like this, okay? So this is reducible because this purple curve is invariant. In fact, like any curve disjoint from the purple curve is invariant. But it is not finite order, right? This is going to be an example of something that's infinite order and reducible, right? Because you can sort of twist as high as you want, and the only way to get back to the identity is by twisting in the opposite direction. But the sort of really interesting part is this part. And it turns out that in a very concrete sense, like in fact there's like recent work of Inyok Choi that sort of gives the other sense. Okay, so in a very concrete sense, pseudo-nosers are the generic elements of the mapping class group. And for a long time this was sort of known in like the random walk sense by work of Maher. And recently in for like sort of looking at balls in the Cayley graph, this is also proved by Inyok, that these are sort of the generic elements. Okay, so sort of the things that you pick out at random will be pseudo-nosem, and these are also the sort of dynamically rich elements of the mapping class group. Okay, but there's something now very powerful that we get out of this classification, right? Which is that not only are pseudo-nosems the maps which have this invariant flat structure, these pair of invariant foliations, they're also exactly characterized as those which are infinite order and irreducible. Okay? So this is sort of a consequence of the Nielsen-Thurston classification. In particular, right, they're exactly the elements of the mapping class group, which, if we take a simple closed curve on my surface and we start to iterate on that, then we're going to get an infinite collection of distinct simple closed curves, right? Okay? Which this gives us sort of another way of thinking about elements of the mapping class group, right? Where I'm not going to spend too long on this, but if this is something you've seen before, it might be familiar. But like because we are getting this sort of infinite collection of essential and distinct simple closed curves, we actually get an axis of translation in a hyperbolic graph called the curve graph. Okay, and so pseudo-nosems can actually be characterized as exactly the elements of the mapping class group which act as loxodromics on the curve graph. Okay, so if you haven't seen the curve graph before, I won't dwell on it too much, but sort of the idea is just that every vertice of your curve graph corresponds to a homotopy class of simple closed curve, and I'm going to put an edge between them whenever these curves can be realized disjointly on my surface. It turns out that this is an infinite diameter delta hyperbolic graph. This is work of Mazur-Minsky, and you can get a lot of rich geometric information about the mapping class group by this action. But the thing I care about is just sort of noting this, that these are characterized by this loxodromic action. Okay, so we've already seen there's sort of lots of ways of thinking about pseudo-nosem homeomorphisms. And there's one more that I want to mention, and this is coming from sort of Thurston's hyperbolization, okay? So I'm not going to state Thurston's full hyperbolization result. He did it in more genericity, but this is just sort of the fibered case. And it says that if we can actually characterize pseudo-nosems in a third way now, right? We already have like they have an invariant flat structure. We have that they're infinite order irreducible. And now we can also say that you're pseudo-nosem if and only if you have a hyperbolic mapping torus, okay? And so, contrary to the plenary speaker's advice yesterday, I am going to attempt to draw a manifold, but it is a cartoon, right? It's a cartoon. But I do believe my cartoon is slightly more accurate than his. So, so what is this? This mapping torus is we're going to think of building it in the same way that you build a torus from a circle, right? You can think of building a torus from a circle by taking a circle, crossing it with an interval to get a cylinder, and then gluing the boundary components to get a torus. I'm going to do the same thing but upper dimension. I'm going to take my surface, I'm going to cross it with an interval to get this mapping cylinder, and then I'm going to glue one boundary component to the other so I get a closed three-manifold, and that's what I'm going to call my mapping torus. Okay? And so when at the pseudo-Nausov, this mapping torus is hyperbolic. Okay, so that is like a really strong thing, right? That we're able to see that the dynamics of this map is determining something about the geometry of this associated three-manifold. And Thurston's proof of this sort of uses the topology that was established in the Nielsen-Thurston classification. It turns out that in the three-manifold setting, right, we're able to sort of determine our geometry using the topology of our three-manifold. Okay, so we have now like all of these different perspectives on pseudo-Nausov homeomorphisms, right? They are our maps which have an invariant flat structure. They are our infinite order irreducible maps. They are the maps which have a hyperbolic mapping torus, and they're the maps which act loxodromically on the curve graph. And so I want to sort of chunk these up into a few different sort of designations. Okay, so I'll think of this as being sort of the geometry, right? We have some invariant flat structure, that's a geometric thing. We have a hyperbolic mapping torus, that's telling me something about geometry, okay? We have topology, right? We have something about the surface topology telling us about the dynamics of this map. If we're infinite order and irreducible, that, again, that's topology. Here, this is also topology, right? The proof that you have like a hyperbolic mapping torus is using the topology of this three-manifold, ruling out like essential torus here. Okay, so again, there's topology happening there. These are sort of really closely related. And then finally, there's dynamics, okay? So this sort of action on a graph and iterating and sort of understanding the long-term behavior, that's a dynamical thing. So is the invariant flat structure, it turns out, right? There's all sort of a whole big field of dynamics that's just dealing with understanding the behavior of translation surfaces, right? Type-Muller dynamics, all of that sort of thing. So like this is sort of also like this very dynamical thing. And so the really beautiful and special thing that happens in the finite type setting is that these perspectives all coincide, right? We have this map, these pseudo-Nausov maps, which encapsulate the geometry, topology, and dynamics all together. Okay, so that's, if there's one thing you take away from this sort of first part of the talk, that's sort of what I'd like us to take away. Is that pseudo-Nausov homeomorphisms are really sort of encapsulating all of these different perspectives in one. Okay. I'm going to pause for questions, because that's the first part of my talk. Yes?
Sorry, you asserted before that a Dane twist was reducible, I think. Did I get that right?
That's right.
And that means there's a finite set of closed curves that it permutes?
That means that there's a finite collection of pairwise disjoint simple closed curves which are invariant.
As a set.
It could be infinite though. Like in the case of the Dane twist, right? In fact, a Dane twist is sort of an identity outside an angular neighborhood of the curve you're twisting. Right. And so in fact you have infinitely many simple closed curves. But you can pick any finite collection of them. In particular, like pick this purple one. That's invariant.
I got you.
Yeah. Yeah, that's a great question. Like you can have more than finitely many, but you have to have that at least.
I see.
And is that invariance under homotopy or just like?
Up to homotopy.
Okay.
Yes. There are people like you may run into another grad student who's going to be a postdoc, Catherine Booth, who has like very cool work studying something called the fine curve graph where you don't have homotopy anymore and like using that to understand like the homeomorphism group. I cannot do that. Like it's scary and terrible and like I need everything up to homotopy so I can make all my pictures nice. So yeah, everything will be up to homotopy. Okay, so what about n-periodic homeomorphisms? So n-periodic homeomorphisms, what I'd like to convince you by the end of this section is that these provide a really nice analog to pseudo-Nausov homeomorphisms once we sort of enter the infinite type setting. Okay? So the infinite type setting can get a lot more wild than the finite type setting. So I have sort of a few examples. You may notice that these are all named. And so that is in fact the only reason why these are on the board in some sense. But there's so many of them that if they have a name, they're a little bit special. So for example, I have a surface called the Cantor tree surface. This is homeomorphic to just a sphere minus a Cantor set. And I could also take that sphere minus a Cantor set and I could accumulate every end by genus. And that would give me this blooming Cantor tree, okay? So here, these ends, I'm thinking of them as sort of ways of going to infinity. And so when I say that an end is accumulated by genus, it means that no matter sort of how far out I go, no matter how close I get to my end, I'm always going to see genus, okay? So it's not planar. Over here I have, so these both have infinitely many ends, right? In particular, they have Cantor set worth of ends. Whereas on the right, all of these actually have finitely many ends, right? I have my tripod surface that has 3 ends accumulated by genus, this ladder surface with 2 ends accumulated by genus, and then this Loch Ness Monster, which has a single end accumulated by genus, right? I do it this way because there's a part of my talk that I'm definitely not going to get to, which this would be useful. But the other reason I do this is because this is sort of a nice hint about like the classification for infinite type surfaces. Like this might not immediately look like a surface. It might not look like this surface in particular. Or like this surface. But it is, and that's because, like, right, if you think about sort of going to infinity in this surface, even though it looks like you have a bunch of ways to go to infinity, you're always going to the same place, right? No matter how large of a connected component you remove from it, you always get just a single component in the complement, okay? So these are actually all homeomorphic by the classification of surfaces. The classification of surfaces of infinite type. So this is a classification that was given by Carrick-Jarto and Richards. Well, Willie was given by Carrick-Jarto and his proof is wrong, and then Richards has a paper that actually gives the correct proof. So it turns out that, as you can imagine, these surfaces can be hard to deal with because if we sort of start thinking about what can happen in terms of the topology of the surface, we can realize any closed subset of the Cantor set as the homeomorphism, like as the n space of some infinite type surface. That's way too much for me. And so what I'm going to do instead is I'm going to focus on much simpler ones like this, where I just have finitely many ends all accumulated by genus. Okay? So they're going to look like this or sort of just keep going, right? You can sort of have more and more ends. This might seem at first like a cop-out to like make things simpler and easier to understand. That's fair. But I would argue that this is a reasonable thing to do because of the following, okay? Which is that these particular infinite type surfaces arise in nature as depth-1 foliations of 3 manifolds, okay? So just like the sort of foliations on my surface, I was taking like these lines and sort of filling up my surface. I was getting a partition on my surface. These foliations for 3 manifolds, I'm now sort of taking 2-dimensional things, surfaces, and I'm going to fill up my 3-dimensional manifold. And when I say that my foliation has depth 1, I just want us to think of this picture. I want us to think that there's sort of 2 flavors of leaves. There's sort of infinite type leaves, and there's finite type leaves. And all of the infinite type leaves have to accumulate onto the finite type leaves, okay? So in this picture, you can sort of think of like you're accumulating here onto this genus 2 surface, and in the other direction, you're also accumulating onto this genus 2 surface, okay? So these are just things that happen, right? This is sort of a way of decomposing your 3 manifold. And it turns out, if we think of cutting along the compact leaves of a depth 1 foliation, we end up with pieces which are now fibered 3 manifolds, where my fiber now isn't like a finite type surface, like that sort of mapping torus picture I showed you before. It's actually an infinite type surface, okay? And so this is sort of the way that you can think of these foliations as generalizations of fibrations, because they're fibered in the complement of the compact leaves, okay? And the thing that I want us to also remember is that not only are we fibered in the complement of the compact leaves, but the monogamy of these fibrations give us something called n-periodic homeomorphisms, okay? And so this is why I'm going to sort of constrict my study to these surfaces that have finitely many ends all accumulated by genus, because this is the setting in which sort of the maps that I'm interested in sort of come up very naturally. Okay, so what is n-periodic homeomorphisms? Let me give you a few examples, and then like try to extract the sort of important parts of them. So the first thing is that I'm going to think of a surface, like my ladder surface, and I'm going to do something called a handle shift, okay? So if we want to define this precisely, think of taking an interval across R, okay, so you get some infinite strip, and at every integer point attaching a handle. And then my map is going to be the one that shifts every handle over by 1, and tapers to the identity on the boundary components. Okay, so my boundary components are fixed. So I can now embed this strip into any infinite type surface that has infinite genus. And if I embed it between sort of two distinct ends, it's going to give me something which is like intrinsically infinite type. So it's not a limit of compactly supported elements. And so in this example, I'm just thinking of taking a handle shift where all of the genus is sort of included in the domain of my shift, and I'm just shifting from left to right. Okay? So not anything particularly interesting going on, right? Any curve that you take sort of over on the left-hand side, after you iterate long enough, it's going to end up way out in the right-hand side, right? And vice versa under backward iteration. I could do something sort of slightly more complicated. Instead of just sort of embedding a single shift, I could embed two shifts. Here I've embedded them in a way so that their supports don't intersect, right? So you can think of these as having commuting supports. And I'm shifting now from sort of both bottom ends up into that top. Okay, so that's another example of something that's M-periodic. And then my third one is a little bit more exciting. I have now, again, two handle strips that I put into my surface, but I now have them having intersecting support. Okay? And so they're sort of passing through this sort of central region. It turns out that this is going to give me a notion of irreducibility that we'll come back to a bit later, this sort of last example. Okay. So what is sort of the key characteristic that all of these examples exhibit? All of them have that under iteration, every end of my surface is either attracting or repelling, right? Like if I sort of iterate these maps, this is going to be my attracting end, these are my two repelling ends, right? Here I have an attracting end, an attracting end, a repelling end, and a repelling end, okay? So these are sort of the key facets. This is, if you want just like the most concise definition of M-periodic, I want us to use that one. Every end of my surface is either attracting or repelling under the action of F. The sort of formal definition is that there exist neighborhoods of the ends of my surface, which I usually call like nesting neighborhoods, so that like when you forward iterate, these form a neighborhood basis of your end, or when you backward iterate, they form a neighborhood basis of the end. And so these two sort of possible situations, these are exactly describing this attracting versus repelling behavior. Okay? But again, so the thing to keep in mind is that every end is going to be either attracting or repelling under the action of your map. Okay, but in order to sort of study these, so you might notice I have some names here at the top. Oh, question, yes?
Like if you go back to the previous slide,
Yes.
in figure 2,
Mm-hmm.
if you specify the green one is shifting the other direction, would that not be admissible?
That's a great question. So it would really depend on like if the shifting was going to be enough to sort of overcome the shifting of the blue. Right? So if you sort of shifted large enough so that like that end was then like repelling, then that would be okay. But if you shifted both the same amount so that one was shifting by 1 and the other was shifting, this would not be M-periodic because this end would be neither attracting or repelling, right? And then this end would be, both ends would be repelling. So I guess it depends a little bit. Yes?
So what if we didn't consider the green part at all? Like there's no shift in the green side. So one end is attracting, one end is repelling, the other end.
So I would not consider this M-periodic. This is a good time to mention. So this work was originally introduced in unpublished work of Handel-Miller, but since then, Cantwell, Coleman, and Fenley have put out, I think in 2019 maybe, like a very comprehensive book that actually sort of develops all the theory. So they actually introduced a notion of M-periodic, where you're allowed to have some ends which are neither, that are just not periodic. And like then everything else that is periodic has to be attracting or repelling. And so like, I guess that end would sort of be periodic. I'm not quite sure because I haven't thought about it too much. I think they allow for stuff like isolated ends to be fixed. And if you have infinitely many, they should all just be permuted but not periodic. But I'm not sure. But for me, it does not count as periodic because I need every n to be attracting or repelling. Yeah. Yes.
So I guess this condition that like f to the m of the neighborhood or f to the minus m of the neighborhood is not contained in the neighborhood, that kind of precludes an n from being like, I guess, like the example that the previous question discussed where you have some like n which is sort of neither attracting nor repelling because sort of nothing happens.
Exactly. That's exactly right. Like you're not going to be able to get like this sort of nesting neighborhood, whereas you forward iterate, you sort of better and better approximate them at the surface. That's exactly it. Yep. Other questions or clarifications? Okay. So, oh here, yes. So in order to actually have some good structure here, I sort of gave myself away by forwarding. I need something more, right, in order to say something. And so that more that I need is some notion of irreducibility. And so I'm going to introduce the notion of strong irreducibility. So this is the sort of notion of irreducibility was introduced again, like in work of Bentley, Cantwell-Conlon, Handel-Miller. This sort of stronger notion is something that myself and some of my co-authors introduced. And it has sort of three things that I'm asking for. It's the same thing that we had in the finite type case. I don't want periodic curves, okay? No periodic curves. But there's more sort of reducing behavior I can see, right? In the finite type setting, we only need to rule out this. Here we have other things, right? For example, we could have periodic arcs. I don't want that, right? So for example, in that example I showed, right, if I sort of take something outside of the support of my handle shift, it's fixed. If I, again, and so the sort of extra strongness that we introduced is that in the original definition of irreducibility, they only ruled out arcs which go between like an attracting and repelling end. We also rule out arcs that go between sort of any ends of any type, so between two attracting ends, two repelling ends, whatever. And then finally, we also want no reducing closed curve. So here, a reducing curve is a curve which sort of starts out in a neighborhood of a repelling end, and then as we iterate, it escapes out into an attracting end, or vice versa. We start out in an attracting end, and we backward iterate, and we escape into a repelling end. So I don't want, this is also sort of reducing behavior that I don't want to see. Sometimes you'll see just this first type of map, where you don't have periodic closed curves, called atoroidal. Okay, so this is sort of an important class of emperiodic homeomorphisms. Another thing that you could think of, the reason it's called atoroidal is because the corresponding sort of compactified mapping torus is atoroidal. And so another thing that you could think of for strongly irreducible is acylindrical. So the reason we added this sort of extra irreducibility condition is because with that, when you look at the compactified mapping torus, you get a acylindrical free manifold. Okay? So that's sort of the things to keep in mind. What are the important things that I need for this, for this talk from irreducibility? I want to talk about that using an example. But again, before we move on, I just want to sort of assure you that there's lots of examples that satisfy this notion of irreducibility. In particular, in work with Hee-Jung Kim, Elizabeth Field, and Chris Leininger, we give infinite examples of these sort of strongly irreducible emperiodics, which there's a little bit more conditions to satisfy here, but the sort of notion, the sort of takeaway is that if you have some compact surface where you put some partial pseudoanosm, so this just means a pseudoanosm on like this subsurface with boundary, and you compose it with a handle shift, that composition is going to be strongly irreducible. Okay? As long as this sort of subsurface sort of separates your ends and is sort of sufficiently large with respect to how much you're shifting. Okay? You don't want to do something silly where you like shift by 5 and you just hop right over that, right? Because then you're going to get those reducing curves. Okay, but the reason I want some notion of some sort of irreducibility is because of the behavior that I want to show us here. Okay? So here's an example that's sort of the form I just showed you, where you sort of are doing something on some subsurface, doing some twisting, and then composing with a shift. And so I want to look at what happens if I take curves which cut off neighborhoods of my ends, nesting neighborhoods in fact of my ends, and I iterate them. Okay? So I want to forward iterate gamma, and I want to backward iterate eta. And so here's, oh, no, I didn't do that. Just spoiled it. It's okay. But right, if I iterate, you start seeing this sort of more complicated behavior. And then I iterate again, and you sort of see even more complicated behavior. So if any of you have sort of studied pseudo-Nassau homeomorphisms, this might look familiar because it sort of looks like what happens when you take a pseudo-Nassau homeomorphism on a surface and you iterate, and as you iterate and iterate, you get something more and more complicated that starts to look like a geodesic lamination. Okay? I'm not going to really define what a geodesic lamination is, but it's going to be the thing that you get by limiting this behavior, sort of just keep going. And so you end up with a pair of these invariant geodesic laminations. And so this is important for me. This gives us a lot of structure. It turns out that that pair of like singular transverse measured foliations that you get for pseudo-Nassau, you can also think there's sort of a whole other way of describing that story in terms of a pair of geodesic laminations. Okay, and so this is sort of replicating that side of the story.
Is the convergence here like convergence on every compact set or something?
Yes. You can think of, like if you want like the formal definition, like think of iterating, actually we'll just leave it at that. We can talk about it more, yeah. Okay. So, this is something that we get for any of our maps, okay? So if we have, in particular, like some irreducibility for a map, then we get a pair of invariant geodesic laminations which fill some finite type subsurface, okay? And so that's important, right? If I looked at my M-periodic thing, which was just a shift, technically I also get like an invariant geodesic lamination there, which is just my reducing curves, right? That also is a very trivial geodesic lamination, and it's invariant. But the extra structure of the irreducibility means that I actually sort of see some subsurface where both of my laminations are interacting with each other. Okay? Yes?
Can you say what the conditions are for irreducibility?
Yes, so for just irreducibility without strong irreducibility, it's just that you don't have any, if everything else is the same, no periodic curves and no reducing curves. The difference is for the arcs. We disallow arcs which run between ends of the same type. If you're just irreducible, you're disallowing arcs which run between a attracting and a repelling end, or vice versa. Okay, and so that is sort of the notion of irreducibility that like Cantwell, Coleman, and Fenley use. So the problem with that notion is those sorts of arcs which run between ends of the same type, those will also give rise to cylinders in the compact fine mapping course, and so that's why we want to get rid of them. Okay. My time is flying. So one thing you can do now is define a notion of a stretch factor, right? We have this notion of stretch factor for pseudo-Nassau, which was that real number that described my action on my foliations. Here I want to describe my stretch factor in terms of this pair of laminations. And so in particular, I'm going to get some Markov decomposition. So this is just some decomposition into rectangles, which has nice properties about like how they map over each other. And so the stretch factor I'm going to define here is just going to be the leading eigenvalue, or the spectral radius of the incident matrix of this Markov decomposition. Okay? And I'm going to call this the Handel-Miller stretch factor. Okay? And so now, again, I want to end this section by saying like n-periodics are good dupes for pseudo-Nassau, okay? They sort of exhibit a lot of the sort of same connections between geometry, topology, and dynamics. Okay? We have why did it do that? We have the geometry of the, let me go back. The geometry of the compact fine mapping torus. I'll mention this very briefly in a second. There's lots of work here. There is work of Fenley, there's work of myself and co-authors, there's work of Langdon and C. Taylor, so Sam Taylor is here at Temple. There's work of Brandon Whitfield, who's here in the audience, and is going to be a postdoc at Madison in the fall. And so there's sort of lots of geometry here. You'll notice we don't have this sort of flat structure picture. I'm happy to talk with people about that after. But we sort of still have this sort of three-manifold geometry. We have topology, right? We have this sort of notion of irreducibility, sort of all of this lamination theory developed by Handel, Viller, Cantwell, Coleman, Fenley. Right? We have this irreducibility, we have these like geodesic laminations. There's lots of topology happening. And we also have some dynamics. So there's like the sort of same type of dynamics as we have in the finite type setting of like looking at some loxodromic action on a graph. There's work of Abbott, Miller, Patel, and Patel-Taylor sort of on this for n-periodic homeomorphisms. We can also think of this, right? There's like sort of lots of dynamics happening here. Like in order to sort of understand the lamination theory, you look at sort of the dynamics on the universal cover, right? You're looking at the sort of behavior there. And then there's lots of dynamics here. In particular, the work of Lane, Dubinsky-Taylor and Brandis-Whitfield, they are really using dynamics of pseudo-Naza flows to get at some of this sort of n-periodic behavior. And I'll say a little bit about that in a minute. Okay? But first, I do want to plug some of my own work. In particular, I want to clarify that this FKLL is actually sort of two different pairs of collaborators. So we showed that if you have a strongly irreducible n-periodic homeomorphism, then the compactified mapping torus is acylindrical with totally geodesic boundaries. And in that case, we have that the volume, the hyperbolic volume of this mapping torus, is coarsely equivalent, okay, to the translation length of our map on the Pants graph of our surface, okay? So this sort of coarse equivalence just means that I have upper and lower bounds with some constant times this, okay? And so these bounds were proved separately. So the upper bound was proved in joint work with Elizabeth, Heejung, and Chris, and then the lower bound in joint work with Elizabeth, Autumn, and Chris, okay? And so I'm very, very happy to talk with folks more about this. I love this work, but it's not what I'm going to focus on next. I want to do a little plug. There's lots of geometry.
Sorry if you already mentioned, but what does the colored region mean again?
Here, this is actually a subtle nod towards some of Brandis' work, in which they're able to understand the geometry of the mapping torus by finding sort of short curves. And one of the ways that they do this is by understanding how some surface sits inside their sort of three manifold that they get from doubling one of these compactified mapping torus. So I can again talk to you more about this later, or you should talk to Brandis, but I wanted to sort of nod towards the different types of geometry happening here without saying too much about it. Yeah. Okay, and so this leaves us with just a little bit of time for the end of my talk, which is to talk about stretch factors, okay? And in particular, I wanted to just mention some of the different sort of dynamical properties and sort of interesting information that's stored in the stretch factor for pseudo-Naza. So for example, the log of the stretch factor, so this is actually the topological entropy, this actually describes the translation length on the space of normed hyperbolic metrics. This is the Teichmuller space. Whenever I mentioned the Teichmuller space, I mentioned that Teichmuller was a horrible Nazi, but he did some cool math. And so this is the space of normed hyperbolic metrics. And also, the stretch factor also describes, so this maybe is reminiscent of the talk yesterday for you folks who were there. It says something about the gross of lengths of curves under iteration, right? So the stretch factor is capturing this growth rate for any Riemann metric on your surface. It also captures information about the growth rate of intersections of curves under iteration. Okay, so if we have any two simple closed curves and we look at sort of iterating f on one of them and like the growth rate of the intersection with the curve we fix beta, we see that that also is captured in the stretch factor. Okay, there's lots more things in fact that the stretch factor captures, but I just wanted to sort of mention these. And this is a quantity that you can compute. Okay, so it's not just sort of something that exists. There's like sort of a very explicit way to compute it. I'm going to gloss over this very fast, but again, I'm happy to sort of talk to folks more about it later. And so there's sort of just three steps to this. You can compute an invariant train track. There's an algorithm for this given by Vespina Handel. You find the transition matrix, which describes the action of your map on this train track. So this is just some smooth graph that's embedded in your surface. And then you compute the leading eigenvalue of that transition matrix. That gives you the stretch factor. So in sort of practice, how you do this is there's some algorithm for doing it. When I actually am doing it, I take a simple closed curve on my surface, and I iterate and iterate and iterate and iterate and collapse and collapse and collapse until I can sort of suss out, I can sort of guess what the invariant train track is, and then once I have a guess, I check that it's invariant. And then I use that to sort of build out the rest. Okay, so this is something that you can actually get your hands on. And we know a lot about it in the pseudo-Naza setting. So in particular, there's a result of Penner, which tells us that for any pseudo-Naza in the mapping class group, we have a lower bound on its stretch factor in terms of the topology of your surface. Okay? And this bound was just sort of proved. There's sort of two key tools that go into this proof. One is a spectral theory trick for homogeneous matrices. So it turns out that that transition matrix I mentioned on the last slide is homogeneous. So there's a sort of nice trick for bounding its spectral radius in terms of the size of the matrix. And then some train track theory. And so the train track theory is to connect the sort of size of this matrix to the topology of your surface. So these are sort of the two things, right? Bound the linear eigenvalue of the homogeneous matrix in terms of its size, and then bound the size of the matrix in terms of the surface topology. Those are sort of the two pieces of this proof. And so what I want to do is see sort of what of these sort of facts about the stretch factor for pseudo-nosons we can recover for n-periodic stretch factors now. Okay? And part of that is going to, so again, just a reminder of what this is, right? This is the sort of this leading eigenvalue of this Markov decomposition that we get in the complement of the escaping point. The way that you can sort of think of it is, again, when you have something that's irreducible, then you're going to get some subsurface where these laminations are actually filling. And so you're going to get some collections of arcs which fill this subsurface. And so you can think of like, what does an intersection of a collection of simple arcs look like? It looks like a bunch of rectangles, right? This is sort of describing for you how you sort of get this Markov decomposition. But it turns out there's another way of thinking about this. So there's a whole, this is the sort of part of, I was talking about when I mentioned dynamics that were related to the three manifold. There's this sort of spun pseudo-Nosov machinery developed by Langevin-Taylor. And so I'm not going to define the spun pseudo-Nosov, there's a lot that goes into that. But the idea is that these give you a singular Handel-Miller representative, and they give you an alternative structure theory for atoroidal, right? So those are ones without the periodic curves, via pseudo-Nosov flows, right? So there's sort of a whole other set of machinery that goes into this. But in this setting, right, you can think of just the normal growth rate that we have associated to any homeomorphism, which is just the exponential growth rate of its periodic points. And so this is what I'll call the spun pseudo-Nosov stretch factor. And it turns out that this is the same. So I didn't know this at the start. Like Chen-Chi and I, who I'll mention in a second, when we were working on this sort of these stretch factors, we were just sort of using this Handel-Miller stretch factor. And because there's sort of all this other machinery associated to the spun pseudo-Nosov, it wasn't clear to us that this actually coincides. But Sam helpfully observed that using some of the work that they've already done, there's a beautiful paper called N-periodic maps via pseudo-Nosov flows, that these actually coincide. And so we actually can say a lot about this Handel-Miller stretch factor using what they are able to say about the spun pseudo-Nosov. Okay, so in particular, they're able to sort of really show that this stretch factor behaves like the pseudo-Nosov stretch factor. So it sort of is the, this gives, like, if you look at the sort of growth rates among all homotopic and periodic maps, this is going to minimize this, right? This is the infimum. We also see that we're getting this sort of growth rate of intersections, similar, and sort of maybe this is nice because this sort of ties back to this Handel-Miller picture I was painting, that this actually captures the topological entropy when we restrict F to some unique invariant compact set, okay? So that hopefully sounds familiar because our Markov decomposition was defined in some complement of the escaping points, which is some invariant compact set. Okay, and I want to point out that, so this originally, this first one, they only showed this for n-periodic maps homotopic to your sort of choice of map, and not sort of anything in the homotopy class. But there's this really great paper of Alice Buckminster, who is here, who showed that, in fact, this can be removed. So this is true if you look at sort of the entire homotopy class. And in fact, Alice also said something about sort of what happens when you look at the sort of the atoroidal and periodic maps as well. So I would definitely check out this paper. It's going to appear in GTD. Okay, so in my last couple minutes, which I'm kind of over time, I just want to sort of mention the work of myself with Chen-Chi Liu, where we're able to sort of give a counter-type bound on now this sort of n-periodic stretch factor. And so it's a very sort of similar flavor. It has some log on top, and then it has this quantity on the bottom, which this doesn't quite look the same. Like what is chi of a map? You're used to sort of seeing this for like a surface, right? And that's the Euler characteristic. This is sort of a notion of complexity, which is the Euler characteristic not of our surface, right? Our surface is infinite type, so like that Euler characteristic isn't a useful quantity. So instead, to describe the topology, we sort of look at the sort of smallest subsurface that we get here when we look at sort of the intersection of these laminations. That's going to give you some minimal core, and so that is going to be sort of the topological piece of this picture. Okay? And then, what? I guess it's saying I'm done, but I'm not done. Did you folks program it to do this? No. So I want to follow sort of the same thing. I want to sort of use Penner's structure, so I want to use sort of this spectral theory trick, and then can I use some train track theory, right? That's what was our sort of initial thing. It turns out that the incidence matrix might not be chrome-phobedius anymore. If anyone has thoughts about how you could characterize when it is chrome-phobedius, I would love to chat with you. But it might not be, right? And this is actually sort of relates to this whole fact that you don't have sort of the same like invariant flat structure that you do in the finite type setting. And then instead of train track theory, it turns out that it's much simpler in the infinite type setting. Because in the infinite type setting, as I sort of mentioned a few times, if you look at the intersection of my two invariant geodesic laminations, and you look at them in this sort of largest invariant compact set, it turns out that these are just consists of arcs. And so we actually sort of can really easily sort of understand the topological complexity without needing to pass the train tracks at all. Okay? So things actually get a lot simpler in this setting. We do use train tracks a bit because we actually, in addition, we show that sort of the growth rate of this bound is sharp. And so in order to show that sharp, we sort of compute this family of examples. But we don't need to use it just to get the bound as a start. Okay, so if you're interested in this and would like to read more, I just want to say that my entire paper is right here. You probably could have read my whole paper in less time than it took to give my talk. So I do encourage you to go read it. It's going to appear in Proceedings, thanks to excellent editorial work by Dave. And so, yes, thank you all so much for being here.
So, if there are any questions for the speaker?
Is there already a similar theory for like out of F infinity, for instance, something like this?
That's a great question. So, like, if you're thinking, so in the big setting of out of n, you're looking at now like proper homotopy equivalences of locally finite infinite graphs. And so in that setting, there is work being developed. So in particular, one of Sam's students who just graduated, Ruth, she has a paper in which she's developed some of this sort of stretch factor stuff for n-periodic graph maps. So that's sort of like the big out. This sort of study was first introduced in work of Lana Vespina and Yal Akram-Fur. And then there's been a lot of work from Hannah Hoganson, George Domat, and Sang-Hoon Hwa that looks at sort of the coarse geometry of these things. But there's also now, another one of Sam's students, Adam Smith, is working on sort of some facts about like being able to develop this thing I touched on, which is sort of this like mapping torus picture for these n-periodic graph maps. And we're also working on something along those lines, in particular like establishing like hyperbolicity of those mapping torus. In that case, right now you're looking at like hyperbolicity of some like feed bicyclic thing. So it's like a very different picture, but it has some of the same analogs, right, that you have in the finite type setting between like mapping class group and out of n. You can sort of try to make parallels now between like big out and like the big mapping class group. Yeah. Does that help?
Thank you.
Yeah? Okay. Yes?
Is there, I believe you mentioned this, but can you say anything about the hyperbolicity of the mapping torus?
Yes, yeah, I'd love to. Why you have hyperbolicity of the mapping torus, or what would you?
Do you?
Yes. So when you have a toroidal n periodic, then you get an atoroidal, so what is the picture anymore, right? The picture, I've been sort of mentioning it, and I had it on my, maybe I'll go back. Like if you go to my transition slides, I was sort of hinting at this without saying it. But like if you go to, I should have put another one at the end. Like here, this picture along the side. So here, right, we start with some n-periodic thing, where you take its mapping towards now, right, you get some non-compact thing. But there's a natural way to compactify by looking at the suspension flow and sort of appending the ideal points. And so you get now not a closed three-manifold, but you get this compact three-manifold with boundary. And so when you are, so the reason that that sort of volume result I stated just for strongly irreducible things, you can state it more generally, but in the case that you're strongly irreducible, so when you have like an actual acylindrical thing here, then your boundary surfaces are not just incompressible, but they're totally geodesic. And so you get like a unique minimal volume hyperbolic structure here. Right, this is very different than what we usually think of for hyperbolic manifolds. Because when we think of like usually hyperbolic three manifolds, we think of Moscow rigidity, right? And so you have a unique hyperbolic metric. But that's not for this situation where we have something with boundary. And so when we have something with boundary, you have like a whole deformation space of hyperbolic metrics. But when you're acylindrical, you get a unique minimal volume one. And so when we talk about the volume, you can think about the volume relative to that. But in terms of hyperbolicity of this, now that you have this sort of nice compact three manifold, you can think of doubling, right? And so like when you get something that's acylindrical, that means when you acylindrical and atoroidal, when you double, then your three manifold is also atoroidal, right? Because you don't have to worry about any cylinders turning into tori. And so then hyperbolicity follows from like geometrization or hyperbolization. Yeah. So that's why it actually is important that we have this sort of irreducibility, because in the same way that in the finite type setting, the sort of topology of your map gives you something about the topology of your three manifold, which tells you about the geometry, the same thing happens here. Yeah. Any other questions?
All right, if not, let's thank Marissa again.
All right,